All right, welcome to IS50B Summer Sessions, Summer 2022. This class builds on IS50A. If you're familiar with the format of IS50B, B is basically the same. However, this class is going to be a lot more programming involved. The 50A class is targeted at people that have never kind of had programming experience before. It recommends you have CSI 40 under your belt. But the kind of programming is like blueprint, visual coding, things like that. In this class, we write actual code. And so the focus on this class is teaching you about the internals of game engines, which is a really interesting topic. And it's also valuable in terms of money, right? Because the highest paid people, I was reading a study yesterday from UK Game Developers Association, that the highest, paid people, not talking about like the owners of the company or whatever, but like the highest paid staff are the programmers, right? The people who make the engines, especially if you know networking. Whereas the artists and the QA people obviously get paid less than the programmers. And so having knowledge of how game engines work will help you to get a job, maybe, if that's your cup of tea in the games industry. And so we're going to talk about something called computational geometry. And we're going to be talking about how game engines work on the inside. And this is going to involve C++ programming. So you will do an Unreal Engine project. You should continue joining in on the IS50A sessions, especially since we're doing Unreal Engine 5 now, and that's a little bit different from UE4. Not a lot, but a little bit. And so during that class time, you can work on a Unreal Engine project to complete that part of your grade, but most of your grade are going to come from programming. Okay, so there's a lot that could be said about how game engines work. There's even if you look at the game engines from the 90s, which are very well documented. Like I think I posted some links on Canvas. Have you guys been on the Canvas yet? Not yet? Yeah. It should be published, so let me know if you can't see it. But yeah, I've put up a breakdown of how the Thief 1 engine worked, which is similar to the Quake engine, but totally different, written by different people, but just kind of similar in idea in some ways. And then there's the Doom 3 renderer breakdown, which is from like 2004, something like that. Thief 1 was like 97, I'm tempted to say, when that came out. And still very, like, 80, no. 98, okay. And still, like, I've never played a game that really replicated that feeling that Thief 1 gave me. I bought the new remake of Thief, and it just wasn't the same. So when I found this article recently, from the guy who wrote the engine, or at least the renderer part of the engine. He wrote this about 10 years ago. I was like, oh, that's cool, and you can see it's not big, it's a couple pages, but you can learn how the engines work, and they're really neat. The graphics programming black book is kind of out of date at this point. Yeah, great, good link. But Michael Abrash is considered by many people to be the godfather of like 3D video game engines and things like that. And Carmack this guy and Carmack are like probably my two personal heroes as far as game engines go and things like that. And oddly enough, I've actually communicated with both of them over the years. Not over gaming, actually. Carmack posted a question on his blog about high performance computing for a specific supercomputer that I was one of 10 people that had access to at the San Diego Supercomputer Center. And so I contacted him. I'm like, hey, I saw your post. I have access to it. You want me to benchmark this thing for you? And so we traded emails. And Abrash posted on his blog, hey, does anyone have any experience filtering the orientation data for a VR headset? And I'm like, I have. I work doing VR video games, and we had to solve that problem too. Here's what I did. And yeah, So kind of cool. Like that's my brush with fame. You know, I've had a pleasant conversation about technical matters with both these guys. So, Abrash was actually brought on board. He was working at Microsoft at the time, but he was brought on board to work on the Quake engine because Carmack was having trouble getting, really the world's first true 3D game renderer to work. So Abrash came on, and the two of them, it's like the dream team. It's like Jordan and Larry Bird or something working together. And so he's been working on VR since then. Anyway, so so these are just names to know. So Abrash, and I'm sure you guys all know John Carmack, right? This guy. It's one of my personal heroes. Collins, have you heard of him before? Ship? John Carmack, guy who made Doom, Quake, Rage, I guess technically. Brilliant programmer. I've watched several of his talks online, and he's just a real sharp guy, and I like him a lot. And his commitment to open source, free and open source software is pretty laudable as well. Basically, they made their money licensing their source code, but after about 4 years, they would just release it into the public domain. And that's something that helped me a lot because I would look at their source code and learn from it. Like one of the best ways of learning how to program a game engine is to look at the source code to a game engine. But if everything was, kind of paywalled, where you had to, pay money for them, which they did, they charged $100,000 or so for their source code. You would never be able to learn. That's in the previous class I was kind of ranting about EA, how they make everybody program in the Frostbite engine, but there's no way for people to learn the Frostbite engine prior to working at EA. Which is a problem, I think, for them. So his commitment to like open sourcing everything is just, very, like I said, he's a personal hero. Okay, so Abrash, yeah, he is a guy. And so I've posted a link also from this guy who talks about how the renderer works for Thief 1. So if you get a chance, go through both of those things. The Doom 3 page, the breakdown on this is actually quite extensive. Like it's in multiple parts. And like it is it's extensive. Like there's a lot to it, but how it works is really interesting. So okay, do yourself a favor, read both those things. I've also posted on here the topics list for this class, and so we're going to be meeting every day this summer. Basically the format is your time and the IS50A time overlap. And so the plan is that your lab time is their lecture time and their lecture time is your lab time, because it's a co-taught class, because there's not enough people in 50B to get its own class, so you guys just are lumped together. So these are the topics that I've come up with for this summer class. If you guys could read through that and tell me what interests you, let me know. I didn't. I was in the process of converting just my notes to a bullet point format. It looks like I got bored and stopped about a third of the way in. So we can review the math behind 3D games. It's probably a good idea. Cross product, dot product, matrix transformations, that kind of stuff. Voronoi diagrams. We'll probably definitely hit that at some point. That falls into the notion of computational geometry. Computational geometry, like the go-to textbook, is this one here by Mark de Berg et al. And it's a fantastic book. It's not, I would say it's pretty reasonable, all things considered. It's not the easiest thing in the world to understand, but it's also not as abstruse, abstract, I don't know the words, as some of the books that I've read on, which are just incomprehensible many times. So we're going to be learning computational geometry as well as game engine design. Computational geometry is doing things like saying, well, if you click on a point on a map, how do you know where the nearest city is? Right. given a bunch of triangles in a map, how do you sort them from furthest away to nearest away? Or how do you cluster them into a polygon, right? So if you've got a bunch of triangles in the world, how do you cluster them into polygons and then eliminate the internal lines? How do you do that? There's a whole bunch of questions that are very interesting in computational geometry. How do you? A big one is, how do you know what's visible? Right? Imagine a warehouse full of blocks. Some of those blocks are going to block. Sorry, some of the blocks are going to block blocks behind them, right? They're going to occlude. It's called occlusion. They block vision, right? And so, how do you know if it's blocked or not? That's a big question, right? Because you don't want to render the things that aren't visible. That's like one of the big ideas, one of the big things for this class is never render things you can't see, right? So if I've got a camera here, I should not be rendering those textures up on the wall behind me. Ideally, I shouldn't process them at all. Like, it should not even enter the pipeline, right? Ideally, that I could somehow filter all of the geometry, all those stickers you see on the wall behind me. A lot of coders have coding stickers on their laptops. I have it on my wall, along with some of my daughter's stickers as well. So if my camera is pointed this way, none of that should be rendered. But then if I rotate my camera, then it is visible, and the stuff this way should be hidden. And that's a big topic, and we're going to be talking about that in this class. So, and that all falls under like computational geometry kinds of stuff, and it's game engine as well. Okay, so intersection testing means how can you tell if something is touching something else? And that's a whole lecture right there. Okay, maybe two. Telling if a point touches a point is pretty easy. Yeah. Does X equal X? Does Y equals Y? Does Z equals Z? All right, they touch. That one's pretty easy. Most of the other ones are kind of hard. A point inside of a box, that's kind of easy. A point inside of a circle, that's easy. Circle inside of a circle is easy. But a lot of them are not. A lot of them are not easy. And so we'll get into that. What is a convex hole? So a convex hole is a term in game development and the sciences and everything. There's jargon, right? So convex holes are, and so this is a pretty common task, right? If you have a set of points, make a polygon that wraps those points in the smallest area possible. It's a great summation, right? So that's a convex hole, right? So you can imagine like a rubber band, and they're like nails in a wooden board, and you stretch a rubber band around them and release it, and it snaps shut. That's a convex hole, and there's actually an algorithm for that. There's several Andrew's monotone chain algorithm and stuff like that. But you can think of a convex hole as just kind of like a polygon that doesn't have any left turns in it. If you're looking at it clockwise, right? So every time you go from one vertex to another on the convex hole, it always turns to the right. Do you see that? There's no left turns. And so convex holes have a lot of really interesting properties, very useful properties for game design. One of which, if you're anywhere within the convex hole, you can see all the walls of the convex hole, right? Because in order for there to be like a dead spot, there has to be a left turn, right? And there's no left turn, so you can see everywhere within the convex hole. That's important. If you're ever given a polygon that's not a convex hole, you can just split it into convex holes. And so most 3D games don't handle non-convex hole polygons. It just splits them until they're all convex holes, and then works with the convex holes. And this is one of the most basic primitives that you work with in game engines. So you've got your point, you got your line, you got your AABB and your OBB. Do you know what those mean? Collins? Bishop? You know what an AABB and an OBB are? Technically, I don't need to say AABB boxes because that's a bit redundant. So AABB is an axis-aligned bounding box. So it is a A rectangle, think of a rectangle where the vertical and horizontal lines are parallel to the x and y axes. Does that make sense? So like, if you make a, probably, whenever you've coded a box in C++ before, you probably made an AABB, right? It's got a min x, a max x, a min y, and a max y, right? That makes sense? And we use those because it makes the math easy. The if you want to see if a point is inside of an AABB, you just say, is the point greater than x and greater than this x and smaller than this x, greater than this y, smaller than this y. Makes the math, makes the code really easy, makes it fast too. So a OBB is a box that could be rotated, right? So and we'll have a lecture on this, but basically let's just reveal the thing. And so you got a line. So an AABB is this axis line bounding box, and something like this is an OBB. Okay. And the coding is harder for an OBB. Maybe not necessarily that hard, or a lot of times you can just rotate it to make it an AABB, then use the AABB code. And then everything has to rotate with it. And so it's, slower, but sometimes if you've got like a bunch of points like this, it's a lot more efficient to wrap an OBB around it like that, right? It's a tighter fit than something like that, which would be like an AABB would like that or something. Okay. Makes sense? You can do that. Circles, you all know. Convex holes, I just explained. A convex hole is a polygon. A polygon with certain restrictions on it, right? So something like this, it's not like an even polygon or anything, it's just a polygon. This would be a convex hole, but something like this is not a convex hole because it's got a left turn, right? All of these are right turns. You turn to the right, turn to the right, assuming you're going clockwise, turn to the right, turn to the right, right? Whereas this has a left turn in it. And so whenever you have a non-convex hole, it'll do that. Whenever there's a left turn, you split it, and now you've got a convex hole here, and you got a convex hole here. Right. So these are the fundamental primitives, the fundamental units that game engines work with typically. You will see the word hole, all over the place inside of game engines. And you're like, what the hell is a hole? What is a manifold? You're gonna go offline? Okay. Alright. So we lost ship. So go ahead and pause the recording for a second. Alright, welcome back, ship. Yeah, these power draws kind of scare me a little bit. It's almost getting to the part where you have to rewire your office to be able to draw enough power out of them all. Okay, yeah. So, what else are we going to talk about this semester? Acceleration structure. So, an acceleration structure, there's a lot of them. Basically, line trace isn't an acceleration structure. It's something you do with an acceleration structure. So, one of the most common things you do in a video game is to draw an invisible line through it, a line trace, right? Shoot a line through the world and tell me what I hit. If I shoot like this, it hits the camera. And it needs to be able to do that fast, right? You don't want to have a situation where like you move 1 centimeter at a time and ask every object in the world, am I inside of you? No. 1 centimeter, am I inside of you? No. It would be incredibly slow. Line traces have to happen quickly. What did I hit? What did I hit? What did I hit? What did I hit? And collision is the other thing, right? So these two things here are what game engines need to make go fast 100%, right? Like you got to make those go fast. Like, do two objects touch each other? And if I shoot a line, what does it hit? If I click my mouse on the screen, you drop a line from, the camera down into the world. Like if you're playing like a strategy game or something, like you line trace down. Oh, you hit the zealot. All right. The Protoss zealot is now selected. All right. So we're going to have a whole lecture on acceleration structures. and how they work, and you might even code some of them. We'll do animation. We'll do AI, and there's a lot of interesting stuff here. These two things here, maybe the first three are Unreal Engine topics, right? Like how do you set up it's called a blackboard, have an AI controller, you know, in Unreal Engine. How do you have them nav around? How do you navigate around obstacles? How do you navigate towards players? How do you do visibility testing? Things like that. And then the other three, and the third one is maybe either way. But the last two for sure are just pure coding exercises. Like, can you make an AI play tic-tac-toe? Right? And if you can do that, all right, can you have it play Pente? I'm sure Ship... You can't hear anything? Oh. Can you hear me, Collins? Is my voice coming through? Okay. Yeah, Ship has done a Pente AI before, but maybe we could do Connect 4, Backgammon, things like that. It's kind of fun. It's a good exercise. Sudoku, word search, puzzle, types of puzzle games. Also generating them could be kind of fun too. But I'm thinking I might actually do that. You're taking CSI 26 in the fall with me, right, Collins? Can you hear me now, Ship? I was typing something. Got it? All right, cool. Yeah, so Collins, are you taking 26 in the fall? 45. Yeah, 26 is the next one, technically. If you take 45, it's going to go with the on. Okay, heads up displays. There's a lot of stuff you can do with UMG. It's pretty cool. You can make widgets on the screen, pictures up here, and life bars and stuff like that. This is a big topic, though. So rasterization. So this is a big part of how a lot of graphics engines work. Like, how do you, at the end of the day, you need to take a triangle and put it on the screen, and you need to put pixels on the screen. The screen is just a giant 2D array, right? And you need to tell it this pixel has this red value, this green value, and this blue value, right? How does that happen, right? That's a whole lecture or two, right? And we'll learn about the old school way of rendering things to the screen. We'll learn about the new way, and by new, it's not really that new, but it's not the old way at least, involving shaders and things like that. And then we're going to learn about a new hot stuff, which is the ray tracing engines and things like that, which is actually arguably older than rasterization, but they haven't been commercially used in video games until the RTX series video cards came out a few years back. And now and even then, the games usually weren't fully ray traced, but they would just use ray tracing on top of rasterization. What does rasterization mean? I should probably define my terms. I hate jargon. I hate it when professors say things you don't really know what it means. Do you know what rasterization means? No, it's still no audio. Okay. Collins, do you know what rasterization is? Still have no audio. How do you? It's strange. I am recording it, Ship. Yeah, so you just watch the recording. I'm not going to talk for too much longer. So if you have a triangle, right? You've heard of it. You don't really remember it. That's fine. So rasterization. You got a triangle, and this needs to be drawn on the screen. Well, it's got to be cut up into pixels, right? So you got pixels on. This is like the pixels of the screen, right? I'm trying to draw this as well as I can. Okay. And so all of these pixels here get shaded in white, right? And this one, because it kind of overlaps, some of the pixel might be in kind of a lighter white. This one here, which is only maybe 15% white, and so it's the process of taking a triangle and actually kind of looping over it and coloring into that giant 2D array we call the screen, or the screen buffer. we write all the color data. The process of going from a triangle to actually putting pixels on the screen is rasterization. Okay, that's rasterizing. It's drawing pixels to the screen. Okay. And oh, you're right. Yes. Okay. All right. So, yes. So that's different from ray tracing. So ray tracing is a whole different can of worms. Like these two things can be used together, or they can be used separately. And so ray tracing is the hot new thing. That's also the hot old thing. Those used to make like old 3D movies like Toy Story and stuff like that. It was all ray traced. So we're gonna have a lecture on that. We'll be doing particle effects, which is kind of fun. Water is fun to mess with. Sprites, 2D sprites rendering. If you've seen like Mario Brothers, like old 80s games, they use sprites. And so if you are into like retro gaming and stuff like that, that's really fun to work with. Maybe kind of fun. Last semester we kind of potatoed on it. So now that we're going to be in person, hopefully, this should be a lot more doable. And then we're going to talk about maps. That's one of the big topics in this class. How do you make a good map for a video game? That's going to be all in Unreal Engine. And then we got lots of other topics that we can talk about, and it kind of just depends on what you want to learn about. I'm always very flexible when it comes to teaching and education, and there's it's a big field, it's a big industry. This is your last semester of game development. I don't have 50C even considered being made right now, so basically if you want to learn something, learn it now. Okay? So that's basically where we're at right now. So what I want you to do for tomorrow is I want you to, and you're going to need to have an account. Collins and Isaac, you both have, you know what's up with the server and everything, right? So we're going to make an account for you. And I just want you to code up tic-tac-toe real fast, okay? So basically, you don't have to do an AI yet, just code up tic-tac-toe. Just make a tic-tac-toe game that can detect when somebody wins. X's and O's, enter a coordinate. When you get 3 in a row, you win. You should be able to do that by tomorrow, right? And then we'll talk about AI tomorrow, I guess. Okay. So that's where we're gonna go. One of the semesters when I did this, like half the people hadn't had me for computer science, and they're like, I don't know. So, yeah, a little 3x3 array, make a little for loop or something. Check for victory conditions. This is actually a common job interview question. I don't know if it's common, but a friend of mine that works at Pandora, he asks, that's his job interview question is, write a function to see if a tic-tac-toe board has a winning state on it. And that's what he asks. So please code that for me. And so that is good practice for you, I think. So we'll call it there. It's already 3:40. And maybe tomorrow I'll turn people loose a little bit more in 50A a little bit earlier, and then we'll have a little bit more time. We'll start digging through these topics because there's a lot of meat in this class to get through. Okay, so that is it, and I will see you tomorrow. Peace out.